So if I say, what do I need in order to make my data-driven decisions? Graphs are one thing, but I also need numbers, or I can use numbers. So there are specific kinds of numbers in statistics that I'm going to use in order to figure out relationships that are important. Now, some of this is, how can I say it, traditional, right? So people are going to have some traditional ideas about how these things work, but they might not actually work, okay? So what I want to make sure is that you understand the different kinds of numbers and which ones are important and why they might be different in different situations, okay? So first off, we want to have an understanding of numbers that go in the center. There are three main ideas here: the mean, the median, and the mode. And most people are pretty well aware of these kinds of numbers and how they work. The mean is the same thing as the average. So to find the average, you just add up the numbers and divide by how many there are. So if I have a data set like this, 10, 15, 16, 19, what would be the mean for that data set? What would be the average? Can somebody tell me what the average is of these four numbers? 15. So if you add them up, you got 60 and divide by 4. So 60 divided by 4 is 15, which is the mean. Now I want to know the median. And I want someone to describe the process. How do I figure out what the median is?
You have to arrange them all in ascending order and then find the middle number.
Okay, that's correct. So we're doing them in order. Could be ascending or descending, right? But we have to put them in order, and then we find the middle number. So what would be the median for this data set? 15.5. So we take the middle between these two, and we could do 15 plus 16 divided by 2 in order to get that number. And then the mode is the one that occurs most frequently, happens the most often. And it's possible for us to have no mode. For these numbers, there's nothing that's repeated, so there's no mode. We can have more than one mode. If we have things that are repeated the same number of times, then it's more than one. Okay? The mode is actually pretty important to us because it's a way for us to say what is the thing that happens the most often. And so then even if we have a histogram or a frequency distribution, so in a frequency distribution, there's such a thing as the modal class. There's actually modes in music too, if you know that, but here we're talking about something else. The modal class, modal means it's like the mode. And so it's the class or the group that has the highest number of data values. And once again, that can be very helpful for us. It gives us an idea of what thing happens the most. Even if it's not 95%, that's at least some piece of information that could be helpful. All right, so then those are numbers from the center. But then we have a problem with these. So I'm going to, and there's information in your textbook about this, but it's helpful, I think, to see how it works. I'm going to change this data set 10, 15, 16, 19, and 300. What is the mean of this data set?
72.
I'm sorry?
72.
72. What's the median?
16.
16. So now, you got to be careful. Sharice, you answer too many questions, and you're on restriction like Scott back there. So somebody else, tell me which one of these two is a better reflection of the center of this data set. Why is it the first one?
Because in the outlier and the second one, that is the changes.
Okay, because when you have a 300 in there, it certainly changes the data set, right? So then the mean clearly is changed very significantly by it. What argument could I make that the median is actually a better representation of the center?
Because more like all the other numbers.
Okay, so when I say what are the numbers like, they are like these numbers, not like the 300. So then if I say where is the center, generally I want to say what is a typical number. But 72 is not a typical number. 72 is actually not in the data set. There is no 72 value. So even though this is the mean, it's not even a possible answer for what I have. Whereas the median is certainly one of my data values. So this is called the resistance of the median. And the sensitivity of the mean. So if we have extreme values in a data set, depending on how they are arranged, they might significantly affect the mean, but those extreme values would not significantly affect the median. So then when we're actually going through a set of data and we want to know where the center is, sometimes we use the median when we expect extreme values that might change things a lot. So the median is often used in two situations. One of them is income, and the other is real estate. Kind of interesting. Just a little side note here, a little bit of political stuff. Anybody out there know who AOC is? Right? So Andrea Ocasio-Cortez recently said, hey, let's do a 70% tax on rich people. It was like, oh no. Well, if we have a 70% tax on rich people, it would actually be a marginal tax so that they'd actually make all the money they wanted to until a certain level, and then everything after that would be taxed at 70%. And so then, you can make a few $1 million, maybe, $10 million, and then everything beyond that 10 million would be taxed at 70%. Well, then you'd have all kinds of strange things that would happen. A lot of people would happen to just make $10 million and the rest of their money just doesn't show up for some reason or whatever else. But it's also true that there aren't enough people that make over $10 million to actually make a dent in our national debt or something like that. Even though there are plenty of people who do make more than $10 million, most people don't. And so then if you tax them at this higher 70% rate, that's not going to necessarily pay for anything because there's just not that many people. They are extreme values. Generally, in order for you to make money in taxation for the government, you have to tax the middle of the distribution because that's where most of the people are, is in the middle. And most people don't like taxes, so that creates problems. But anyway, income is not an evenly bell-shaped distribution. There are plenty of people who make $1 billion. Okay? Here's $1 billion. There's a million, here's $1 billion. Okay? If you have somebody who, say, is in extreme poverty, they might make $1,000 in a year. That would be extreme poverty, right? How many poor people would it take to make one rich person? What's the ratio here?
Four to one?
No,
The 3 to 1.
no. If I take this number and I divide it by 1,000, what do I get?
Maybe 1 billion.
$1 million. So it takes 1 million poor people to equal one rich person. That's a lot of people, right? So then if you say, if I just want the average income for a place, then I'm not going to get a really good reading if I use the mean, because the mean is so sensitive, it will be changed by these very high numbers. So if you're going to compare, for example, La Crosse to Madison, Wisconsin in terms of income, you're going to use the median income in order to do that. And the same thing is true for real estate. Is it possible to have a house that costs more than $1 million? Yes, it is. You don't have houses that only cost $1,000 generally. But still, if you have $1 million house, that's worth like a bunch of other houses. And so you don't necessarily want to include that in your average. So you want it to more reflect the middle in a resistance situation that it's not going to be affected by those extreme values. All right. So that's a helpful thing to know. Then we have numbers that talk about the position of the data. Those include these words: percentiles and quartiles. There are many situations in which either a healthcare provider or a teacher or someone will be talking about percentiles. Phew, pardon me. So let's say that I am in the 80th percentile in my chess playing. If I play chess, I'm in the 80th percentile. What does that mean? It means that I am better than 80% of the people. So if you're in the 80th percentile, you are higher than 80%. And so they'll talk about this, especially with children in the development. This child is in the 30th percentile for height. Well, that means they're shorter than average. And then you can do that for all kinds of different measurements. We're not going to do this, even though it's something that you might run into. In order to calculate it, it's kind of complicated and it doesn't really necessarily help us that much. But we are going to talk about the quartiles. Let me get the eraser here. That the idea of quartiles is a way that people in the past used a lot to understand data sets. And what does it really mean? It means that we split up our data, and in the middle, of course, you would have 50% of the data on either side. That would be the median. But then we split up those sections of the data so that we would have the low 25% and the high 25%. And then each of these things would be a quartile. So the number here would be Q1. This would be Q2. This is Q3. Q4. It turns out this would be Q0 down here. So Q1 would be that number, which would give us the bottom 25% of the data. What value would reflect having 25% of the data lower than that? So in order to make this happen, we want to find these quartiles. Q1 is defined to be the median of the lower half of the data. And then Q3 is the median of the upper half. So, in doing this process, then, it's going to give us an idea of where or how the data is distributed. Now, if we take an actual data set, which we can here, so I'm going to use the data set from problem number 8 on page 111. And what we're looking at here then, if we have a dot plot, you can see where the different data points are located. But then if we do a summary here of the statistics for that, where are my quartiles? There we are. So I want the minimum, the maximum, quartile 1, quartile 3, and the median. Okay. So if I'm looking at this, down here is my minimum, 13.4. The median is here at about 18. So then I would look at this set of numbers, and I would want to have them all in order, and I would figure out the median of the bottom half. And then I would look at this set of numbers, and I'd look at the median of the top half. It's very helpful if you use technology for this. You can just click, and there it is. Or if you want to see it more clearly by hand, you could sort the data and then count the numbers and make the medians and all that stuff. Okay? Not absolutely necessary. If you can do it on here and just click it, make it happen, then that'll work. And again, for StatCrunch, it was statistics, stat, and then the choice summary stats and columns. Okay, so stat, summary stat, and columns. And then you can find those different things. Any other question about this so far? Okay. The big deal with this then, if we say why are we going to use this, how it's going to be useful for us, it's something called the box plot. The box plot is a graphical way to show the distribution of our data by using, actually what used to be called a box and whisker plot. Because we're going to have a box, and it's going to have whiskers on it. So when people started using this, it was like, oh, that's too unclassy to say box and whisker. So we'll just call it the box plot, even though it's really a box and whisker. So if we do that, we click on that on the graph menu in StatCrunch, box plot, again, select the column. And there are two things that I do here. I don't use fences because we don't need to know how to do that. That's okay. And then we draw the boxes horizontally. You can do them vertically or horizontally. It's okay either way, but I find it more normal to do it horizontally. So this is a box plot. What does a box plot have? It has a box, and the box goes between quartile 1 and quartile 3. And I think I might just erase my stuff here. So when we look at this, we see that the minimum is here, and then quartile 1 shows the bottom of the box. Quartile 3 is the top of the box, and then this is the maximum. The median is indicated by a line in the middle. Now I'm going to hope that you can do a little bit of thinking here. How is this useful? What can I get by looking at this box plot? And the answer is I can get an idea of how the data is spread out. Each one of these 4 sections includes 25% of the data. And so I can see pretty clearly from this that the right side of the graph is spread out. And so this is another indication that this is right skewed. So one way that I can know if something is skewed or not is by looking at the box plot. If that right whisker is way longer, then that's telling me that it's a right skewed set of data. If we're not, if they were pretty much the same on both sides, then I'd say, well, it's kind of symmetric. Any question about that right now so far? Okay. But then, if I ask the question, is this helpful for doing actual statistics? I say no, because it's not showing me where 5% of the data is or 95% of the data. So I don't get good information about what to expect from my data by looking at the box plot. Unfortunately, the textbook loves the box plot, and they'll put them all the way through, and they'll say, oh, interpret the box plot in order to understand what's going on. And I say, no, that's not really going to work, because the box plot doesn't show us that 5% or 95%. It's showing us 25% in each one of those categories. So, for example, inside the box, there's 50% of the data in here. Well, there's just as much data outside the box as there is inside. So it's not really telling me what to expect in any reasonable way. But it's traditional, and so everybody uses it. Or they used to. Now, many research papers are just showing dot plots so that you can see where all the data is located. Usually better to use that instead. All right, so these measurements that we have, there's other things that can be used, like something called the IQR, which is Q3 minus Q1. Again, may be useful to understand how much the data is spread out, but not necessarily that useful. All right. So Question?
I left the flash drive.
Oh, yeah, come on in.
Sorry.
All right,
Thank you.
good job. All right. I certainly prefer to have people find things than not, so. Okay. But all this that we've been doing up to this point is just kind of introduction to the real thing that we want. The real thing that we want is not the center of the data. Center is bad. Why is the center bad? Because the center does not tell us what to expect. The center tells us the center. And as we saw from that other data set, if I use 72 to find the mean, that's telling me nothing really. If I use 16 as the center of the data, that's not really telling me anything, right? Because it didn't tell me anything about that 300. But as soon as I try to include the 300, it messes everything up. So the center really doesn't tell me what's happening. What I need is the center with the variation. That is what I want. Okay. I do not just want the center. I want the center plus variation. And I told my colleague that I was not going to tell the story, but I'm going to. All right. So it's on YouTube, so that'll make it interesting. Let's just say that someone was going to evaluate someone else's performance. And let's say they gave them some kind of a goal to shoot for. Like, you're now at a 6, I want you to be at an 8 in 5 years. Does that sound somewhat reasonable? If it's a number that's supposed to go up, and you're at a 6, I want you to be at an 8. Well, it seems somewhat reasonable, right? Unfortunately, this is a particular measurement that has a lot of variation in it. This number could go anywhere from 2 to 12 in one given year. So what sense would it make to say, I want you to go from 6 to an 8, when historically, this number can really be all over the map. It can be anywhere, and there can be all kinds of reasons why that number could change. So here you have something that might change, but the number itself is not in control, okay? There's no way you can say what you're going to do is actually make this number change. There's too many other things going on. So it makes no sense for you to give someone a goal which could be attained or even exceeded randomly, or could be a complete disaster, and it has absolutely nothing to do with what the person is doing, because that number just changes so much inherently to the number. It makes no sense to put your standards based on a number that's constantly changing and it's widely varying. Unfortunately, management does that all the time. They say, okay, well, we're going to set a goal for sales, and we want to have a 20% increase in sales. Well, how much of that 20% increase is actually due to the behavior of the employees, and how much is due to things that are outside of their control? If you don't know the answer to that question, then you have no business making it a thing you want your employees to do, because you don't know that that's what they're doing. It'd be like saying, oh, you know what, my goal is to have fewer thunderstorms in August. I can't do anything about that. Oh, my goal is to have more rain coming into the the water treatment plant, or less rain. I want less rain going into the water treatment plant. Are you in charge of the rain? You are not. You might be in charge of the water treatment plant. That's great. But you can't be in charge of the rain. So you can't set a goal based on things you have no control over. That's why you need to know the variation of a number. And not just you need to know the variation, you need to know where the variation is coming from, okay? So setting goals for people and saying, well, we're going to set this as our goal, you have to know that there's something you can actually do to make that happen. Otherwise, it's pretty pointless. And then when you are at a meeting and you have people handing out these numbers and there's like 20 of them, and they're like, well, these are our goals for next time. And you're like, do we have coffee for this meeting or what? Afterwards, okay, okay, afterwards. So, yeah, like I might have said in the past, statistics is dangerous because once you start looking at it, you start to see how numbers actually work. And then once you see how they actually work, then you're like, people are doing things they're not supposed to be doing with numbers. So don't do that. And if somebody tries to do it to you, then you can send them to me and I'll say, don't do that. Because that doesn't work. So how can we measure the variation in a data set? Well, one way we could do it would be to use the range, which is just the maximum minus the minimum. But as we just saw, that maximum number, if it changes drastically, that's not necessarily changing our data set. It's just changing the number at the top or at the bottom. So the range is not very useful. So what we need is something that we can use that's going to include all the data, and it's going to somehow measure the data in the change. How much does it change, goes up and down. And we have what is called the standard deviation. What does the standard deviation do? It measures the variation of a data set from the mean. Okay, this is really important. You need to know this. Standard deviation measures the variation in a data set from the mean. As I said at the very beginning, variation is the key to understanding statistics. Numbers are constantly changing. If the numbers were the same all the time, we would just use a formula or something, but we can't because the numbers are constantly changing. So we have to have some way to describe the behavior of the numbers, even though we don't know what they're going to be. That's what we mean, what to expect. We want to know what to expect because we don't know exactly what's going to happen. But what can we know? Well, we can figure some things out. So this is important. We need to know how much variation there is in the data set. If it looks like this, this would have a smaller standard deviation. If it looks like this, it will have a larger standard deviation. You can take a note that they could have the same average, these two data sets, but they could have a very different standard deviation. Standard deviation is going to help us to know what to expect in this situation. Now, the formula for a standard deviation is relatively complicated, but I want you to be able to use it. In fact, one part of the project is going to be, I give you a set of numbers, you use the formula and show your work so that I can see that you know how to do the standard deviation. However, if you ever get stuck, you can just click StatCrunch or do some stuff on Excel or use your graphic calculator, and it's very easy to get the standard deviation using technology. But I want you to know how to do both, all right? So this is what the formula looks like. And it's important for you to understand that this is the sample standard deviation. Most of the time, we are working with samples. If you look through the PowerPoint or look through the chapter, you will see that there's a different formula if we're doing population. But if we're doing sample, this is what we have. And if you're going to use technology, you have to make sure that you're using the correct commands so that you have the sample standard deviation. Okay? So there, I'm sorry?
Sorry, is that x minus x?
No, it's x minus x bar. Okay? So we need to go through these symbols and what they mean. And then there are 6 steps for doing the standard deviation. S is, of course, the standard deviation. What does the letter X represent? In statistics, the letter X represents a data item or a measurement. In a given situation, we do not have just one number, which is X. So, for example, we might have a data set where X is 3, 7, and 10. Sorry. 3, 7, and 8. So that means I have 3 different values that are all called X. In fact, this would be X1, X2, and X3. What's X bar? X bar is the mean, or the average, of my numbers. N is the number of measurements, or the number of data items. Notice that when I do this formula, I'm going to be dividing by n minus 1. I do not divide by n, I divide by n minus 1. So, here are the 6 steps to finding the standard deviation. Number 1, we find the mean, X bar. So what's the average of 3, 7, and 8? 6. So in this case, X bar is equal to 6. Then we're working from the inside of the formula here. We're going to take each data value and subtract. So we're going to subtract it from each data item. What's 3 minus 6?
3.
Maybe 3. What's 7 minus 6? 1. What's 8 minus 6? 2. So now I have 3 things here. The subtraction does not just happen once. The subtraction happens for each of my measurements. I then square those things. What happens if I square negative 3? It's a positive 9. Notice when I square negative, it's positive. This is 1, this is 4. What is that symbol in front of the parentheses? This is a capital sigma, and it means to find the sum, or the total, which means we need to add them up. So step number 4, we add them together. So that, in this case, would be 14. That's going to give us the top of our fraction. So I'm taking the square root of 14 divided by 2 in this situation, or 3 minus 1. There are 3 data values, so I divide by 2. So I have the square root of 14 over 2, which is the square root of 7. What's the square root of 7?
1.
Nope, square root of 7.
0.6.
2.6 approximately. So that is the standard deviation of these 3 numbers. And notice it's in the neighborhood of these subtraction numbers here. Okay, so that's the standard deviation. Now, what we did not have time to work on was the empirical rule, z-scores, and Chebyshev's inequality, right? So we'll talk those next time, although you'll need to work through what's in the PowerPoint presentation in order to be able to understand how those work on your homework. But for the quiz, all you need to know is how to do the box plot. So hopefully we'll be all right with that. And then we'll talk about those other things next time we get together.